wear the mic and say something also?
Yeah, sure. So here's the map. So I will test.
When I watch it, I want you to do it.
Yeah, I know.
I'll bring it. Okay, so where do I go? Do you have a test link or the regular link?
Regular. Yeah, regular one. So here's go live 1 minute already. So you can go live.
So this initially it'll be the seminar.
Okay, here's the map.
Would you like me to
To review the latency.
you know,
It's not real time, but it's 10 minutes. Not 10 seconds latency.
Oh, sorry, this I don't want right now. Take this off for now. After this is done, I wanted to show up the main screen.
So what do you mean by after that?
So after the first hour seminar, there'll be like a discussion. And I want to have this image on the screen.
Oh, okay. That's fine. So, but what about the video? So you want the video at that time too, or?
Yeah, no. After that.
After that, only
After 1
your
hour,
image.
everything is done. Just the image from that computer to the screen.
But it keep living.
Don't even worry about it. Nothing. Cancel everything. Close everything down.
Okay.
So we don't need. Okay.
Yeah,
I got
just take
you.
the image off of this screen.
I like them.
Can you talk in the mic a little bit?
I just use. You listen because we talk.
What about the video?
Take
So you
this.
want the video at that time?
Right.
Yeah, no,
Perfect.
after that, only
I
your
want to
image.
make this just the image from that computer to the screen.
But it keep living.
So can you pause the, cut the sound down for now until we start? Just mute it.
Okay. I mute the sound.
Yeah, I mean, she's really
Oh, it's like 12. It's a little bit behind. Okay.
And do you think that we should add her to the panel, or do you think it's too far outside of the scope?
I would do whatever Natalia's comfortable with, honestly.
Okay. I did add Q, because I think he's at charge. Because he's also going to talk about DOT. Maybe at some point I would like to talk more about
Well, today was too crazy, but
I know.
I wanted to talk to you in general about the event series. Like, I know Simon had asked us to do some stuff, and I've just been way too busy this week, so.
I just
And I saw you put Don on, which is great, but I think we need to like also actually, between us at least, like figure out what the heck we're doing and figure it out.
Yeah. So maybe we can, maybe you and I can figure out a time to
Yeah.
Okay. Maybe like
Just not this week, yeah.
Yeah.
Two major RP deadlines.
All right. Well, good luck with that. I saw you
I browsed it, but I just put it off.
Yeah.
Was there a deadline coming up for anything?
I just thought it would be an interesting process for you.
Okay. Thanks. Does this zoom a little bit, or does the fixed zoom?
Yeah, the fixed zoom. So here is just twisted.
A little closer.
Okay. There's no the desk, so I can only see the monitor.
Yeah, I mean, she'll use the.
So here you can see there's no the desk. It's the half.
That's good.
That's good. Okay.
She's not gonna stand at the desk. She'll stand a little to the left.
Okay.
Anyway, you have to just adjust it while she's talking. Because you're gonna change the slides also, right?
Yeah. Right.
So while she's talking, you can adjust it if she moves around too much.
Okay.
Yeah. I'll still make it on it. So you can set your off up here, and is this a good place to stand? And you can change this orientation of this table. The only thing is the HDMI cord only goes so far. I'm not gonna plug this until we actually start, so that we don't kill people. But.
Yes, hi, I'm Sarah Catherine. We emailed this to you. I'll be doing the panel later. Okay, great. Yeah.
Lily's a polygraph. Everyone can see that.
Oh, yeah.
So we're very excited to have her here.
Okay.
Those guys are completely different.
Yeah, it's pretty different.
And so is Jack.
Yeah, I knew that.
Did you know that?
No.
What?
She's the one with papers, right?
Correct. Yes. And then if you wouldn't mind wearing this microphone. I have a clicker if you want to use it. The pointer doesn't work on this screen. The pointer on the pointer. So you use your mouse or pointer or whatever you want.
Could you sign up for
So, oh yeah, the seminar is open to everybody. So there might be names that aren't. So that's for after the seminar. Abhi, what's your experience with this?
Okay, Derek, you're missing one word.
Three remotes?
Yes, three remotes. And the third one was.
Put this away.
Please don't block the the camera. Yeah. Take care.
Welcome back. Anyway, good luck.
You put it on the HDMI that works with that. No, just change the source. I would say it's quite safe. It was plugged into the Apple TV cord, and I just moved the HDMI cord. So it was working. Well, it's not even on the main source now. It's on the computer source. So we need to switch the source first. They're on. We can't change the source. Okay, so let me just carefully stop. Can you take the HDMI out of the computer? Can you take this HDMI?
Hmm? Yep.
The setting was sponsored by Skillshare. I would like to try them out.
No, but I moved it onto the PC. It's not on the computer.
Enjoy.
Just give me now the TV screen. Okay, so now it's working. So you want to connect? Well, let me know the problem's on. Why don't we connect to?
And you're going to go over to the audio or devices out there that your microphone is being picked up for this video. Captures like music and everything. You'd be able to also, now that I have this selected, is this video with, and I'm using this in Audacity. So now that I have this selected, it's picking this up right here. This is very self-explanatory, very easy to set up. There's not too much that goes into it because in your properties, you just have this. There may be other properties depending on if you add something else in there.
To the screen.
Good, how are you? Mine or?
Yeah, it's working from that computer. We plugged it into yours for some reason. So.
Feel free to sit wherever. It looks like front row or back row are the options right now. Yeah, it's back
Just in case we might have to ask you to switch the slides to that computer.
Yeah, they're still setting it up. So
He has the slides already, so.
You did. Give me the flash drive.
What?
Flash drive.
Flash drive
With the slides. You didn't copy it to the desktop?
I copied to. Oh, you.
I need to put the slides in there.
Okay. Didn't copy the.
Actually, yeah, I saw like yeah, where are you? Other than and then there's an advocacy group where there's a voting they have like a really small policy sheet and then just write it to us.
Oh wow. That must be.
Jenny wants to not do it.
Yeah, it's
Jenny not to do
one of those things where it's kind of just like really good. Sometimes these things like get happen like not really done by accident. Like right now, we're working on a healthcare line sciences report, which we've gotten a lot of input from members who are experts, but at the end of the day, like, I'm sorry. And so it's kind of.
Good job, class.
I know they let me out early.
Finish early?
Yeah. But yeah, it's kind of fun.
Yeah. That's.
Yeah.
They've helped.
Yeah. I mean, a lot of people like really do that. There's that's numbers, so we're not even sure the decision, but
Yeah.
Take the good well. Okay, it's back on the computer now?
I've been working on there since June. And the original data was actually really separate from that. We wanted to was like, yeah, it's really totally. But
Yeah, some of that. You'll get it.
Are you looking? It's like that. Size of the systems.
Can you see?
Oh, that is exciting. I'm sorry. That's okay. I think partially I was
The videos are working, at least that's good.
Oh, okay.
So I think we'll have to use this.
Okay.
Let's start.
Wow. Or they're gonna like.
The mouse.
And it's funny.
yeah, it's super cool.
I just came from Washington.
Is it working?
Today. Sorry, I'm tired.
Sure.
She's gonna go around the class and ask the other one. It's pretty crazy. Yeah.
Are you okay with using the clicker?
We're like, I already worked with the DOT, I still want to work better.
It works? Okay.
Yeah.
I think so. Sorry, you have to point it out. You might have to point it down.
You guys want when I had a student viewers.
Okay, sorry everyone. Thank you for coming. Sorry for the technical difficulties in starting late. I want to introduce Professor Lily Elefteriadou. Is that right? Okay, she's she's a professor at University of Florida and director of their USDOT Regional Transportation Institute. and I'll let her tell you a little bit more. But the exciting thing about bringing Lily here is she's one of our alumni and a distinguished alumni. We presented her with the Distinguished Alumni Award this year at TRB, for those of you that were there, you remember. But Lily's also an expert in transportation engineering and has a very pertinent talk to most of our students, especially with the stuff that you're working on. So take it away, Lily.
Thank you very much. It's a real pleasure to be here. When I was a graduate student here, none of this existed, so it's really nice to see the way Metrotech has evolved. And I got a great education here. My advisor was Roger Ross. Worked also with Bill McShane, and my area is traffic engineering. So I've done a lot of work with traffic simulation and so on. The topic I'm going to talk about today deals with autonomous connected vehicles and optimization of vehicle trajectories jointly with signal control. Before I go into the research, I want to tell you a little bit about the UF Transportation Institute at the University of Florida. We're located in Gainesville, which is where the UF campus is. Anybody been to Gainesville? We're about 2 hours north of Orlando and about an hour and a half from each coast of Florida. So we're right there in the middle. With climate change, we're probably going to be waterfront property, but that's probably coming soon. So with the UFTI, we're doing research on, we have several research groups: autonomous connected vehicles, data analytics, safety, human factors, sustainability, and infrastructure. And we also have two auxiliary groups. One deals with technology transfer more specifically, and the other is McTrans. Have many of you used the highway capacity software McTrans develops? Some of you may have.
It's yes for us.
So McTrans is part of the UFTI. As Sri said, we also lead the regional University Transportation Center with 9 other partners. We are the lead for the Southeast, and we are focused on congestion mitigation. So a lot of the research that we do deals with congestion mitigation. So with respect to the project I'm going to talk about, we started it 4.5 years ago. It's funded by National Science Foundation. And since then, we have gotten additional funding from FDOT to expand the scope of what we're working on. And the basic idea is that for signal control, for an isolated intersection, we are able to detect vehicles as they arrive within a communication range of the intersection. We collect information from conventional vehicles through radar and video and so on. We also collect information for autonomous vehicles through DSRC, connected vehicles as well. And the algorithm processes that information and optimizes the way the signal allocates the green, so the phasing, the timing, and also the trajectories of autonomous vehicles which are able to receive those optimal trajectories and execute them. So the optimization is jointly for autonomous vehicles, which are able to receive trajectories and execute them very in detail, very accurately. We also produce trajectories for connected vehicles. So as a driver, if you have a device that allows you to receive those messages, you can establish the speed at which the vehicle needs to travel. And we're also taking into account conventional vehicles. We also developed a simulation environment using Vissim to evaluate those. And the project also has a transition to practice component, which is where we are right now. And so we have instrumented a signalized intersection on the UF campus, and we're getting ready to deploy and test the system. So I'm going to talk about research findings and also the transition to practice. It's quite a large research team. My background, of course, is civil engineering, but we're also working with mechanical engineers, and they're the ones who have the autonomous vehicle technology and computer science. Carl Crane is the mechanical engineer, and Sanjay Ranka is from computer science. And from computer science, they're dealing with the sensors, sensor fusion. How do we get this information and predict and obtain accurate information about vehicles? And several graduate students from different departments, 3 or 4 of them have already graduated, and a couple of undergrads. We also have, we've been working with ISS. I don't know if you're familiar with the company that developed the otoscope, but they're providing more support from the sensors, radar, video. And I should say also that Econolite is a partner, and they've donated a controller and are helping us with the signal control aspects of it. Have you been working on autonomous connected vehicle research? Yes, some of you. Okay,
No,
so
half the room.
half the room, they're just shy. You know the capabilities of autonomous and connected vehicles. With autonomous vehicles, you have sensors on the vehicle. You're able to detect where objects are, and when you have connectivity, you're also able to communicate and get additional information with respect to even units of traffic you're not able to see through your sensors. So coupling that with sensor technology gives us a great opportunity to be able to do signal control a little bit better. How many of you have worked on signal control optimization? Actuator control? Some of you? Yes. So with actuator control, we only know where vehicles are located, but we have no way of guiding them in a particular way. So with connectivity, we're able to do that and improve generally operations. So, like I said, the objective is to develop optimization algorithms that take advantage of automation and connectivity, and to develop a simulation environment. So we're able to test the way the algorithm would work under a variety of scenarios, and so prepare then the algorithm for installation in the field. And the sensors and sensor fusion is a big part of how this can be done. So I'll talk about each of those components in a little more detail. This is the concept overall and how it is implemented. We have vehicles that have the capability to be autonomous and connected, so they have both in one vehicle, and so they are able to send information and receive information, so they can receive optimal trajectories. With connected vehicles, they are able to exchange information about their location and so on, but they are not able to execute that trajectory only to the extent that the driver is willing to accept their recommendations. And then with conventional vehicles, we have to have a way to detect them and incorporate that into our algorithm, and we can kind of predict where the vehicle is going to be in the next time period, but we have no control over that. So the information we're collecting is through LiDAR, radar, and video, and DSRC. All that is being fused, and this is where the computer science group has been working on. And so based on the sensor fusion, we're able to get the best estimate of vehicles' location. The information on vehicle arrivals is the input into the algorithm, and the algorithm generates optimal signal timings, which go directly to the controller for implementation, and then optimal trajectories, which are then transmitted to the autonomous vehicles, which can execute accurately, and connected vehicles which are receive recommendations on what those trajectories would be. And this is the data flow and the information that is provided from one component to the other. Which is, and I'll have to tell you that one of the major challenges in doing this is that you can do this in simulation, but when it comes to actual hardware and software, it's much harder to make sure that all those communications happen and, for example, getting the information from the algorithm into the controller requires several steps in coding to make sure that you that you send the information in a format where it's going to be recognized. A few words on the optimal trajectories. When you have a vehicle arriving, in order to provide an optimal trajectory, you need to know where the vehicle is going to go. And of course, if it's going to turn, you have more constraints in terms of the maximum speed the vehicle will have as it's turning versus if it's going through, where you can maintain a maximum approach speed. So when we first started doing developing the algorithm, we started from a very, very simple two approach intersection, only through movements and complete enumeration for optimization. And you can do that if you only have two movements and you have only two phases. And so that was kind of it was a challenge even to create that optimal signal control and trajectory information. Then when you have turning movements, you increase the complication, because now you, like I said, you have to have the intent of where the vehicle is going to go, so that the trajectory that you provide is going to be have a maximum speed. And so the way we are setting up the trajectories is in a way where you can have the vehicles departing from the stop bar at the minimum headway and at the maximum speed. Maximum speed would correspond to the particular movement. And in this way, you maximize the throughput. Is everybody familiar with saturation headway? What the saturation headway is? Yes. So the first example and results I'm going to show you deal with a four-way intersection with turning movements. And so this was simulated initially for 100% autonomous vehicles. So all the vehicles are able to execute the trajectories as they receive them. And in that situation, you don't need the conventional signalization. You can just optimize the vehicle movement without accounting for things that we have for conventional vehicles, the yellow and all that. So, and by the way, at the time we were starting with this, there was another group at the University of Texas working on a reservation type system, where they were, the vehicles as they were approaching the signalized intersection, they would send a request to the intersection to use a particular area of the intersection. And if the location was going to be occupied, then they had to change their trajectory. And we've done some interesting comparisons between the two. The difference in ours is, as I said, we are providing optimal trajectories to the vehicles. Okay. So the overall algorithm in this case, and it was developed, the optimization was based on genetic algorithms, was based on calculating the trajectories of a lead vehicle versus trajectories of following vehicles. And another important concept here is the optimization horizon. So you've seen time-space diagrams, right? Familiar with time-space diagrams? So this, on the horizontal axis here, shows us time, and these are the green, red for that particular approach. This gives us the distance, and so we're optimizing for this interval. We're collecting this information for the first interval, and so based on this information, then we are projecting what the time intervals are, what the signalization is going to look like a certain time later on. And so the way we are we're implementing the optimizations, we have the first stage where we have initial information about arrivals and kind of predicting what's going to happen for that interval, and then we are re-evaluating at this interval and then at this interval and so on. So this is based on the principle that you have already arrival information at some time where you can project and anticipate what the signal times are going to be at some time in the future. Obviously, the shorter this distance is, the less time you have to change anything in the trajectories. And so I'll come back to that a little later. But that's the idea. And then the departure headways, as you can see, are grouped during the green. And so for a particular set of demands, you can manage so that vehicles don't have to stop. So you are adjusting the trajectories and grouping them so that they can depart within the green. And again, you cannot do that with infinite demands, right? You have to get you can get up to a maximum of whatever your headways allow, the minimum safe headways that you have set, and the demands from the different movements. So the optimization process, again, this is for autonomous vehicles, is based on a genetic algorithm-based optimization. And I'm going to show you some results. Again, keep in mind that this is all 100% autonomy. So this graph shows average travel time, and this one throughput. And the comparison is between actuated control using simulation versus our algorithm. The horizontal axis shows flows. So we're starting from, this is balanced demand, so each approach has approximately 200, 400, and so on. And then the horizontal or the vertical axis is showing the delay. So for lower demands, you don't see much of a difference whether you have the system or not. It operates similarly to the way an actuated controller would work. Where it starts to make a difference is when you have the higher demands, and so in those cases the delay drops significantly. So we, based on our simulation experiments, for some scenarios the delay dropped by 80%. Keep in mind that this means, though it's 100% autonomy, that means no yellow. So you're gaining some from that. Some of it you're gaining from the lost time. So you don't have lost time due to reaction and all that. And similarly for the throughput, again, we're comparing actuated control to our algorithm. When you have low demands, it doesn't matter very much. You can't do much to increase the throughput. It is what it is. But then when you get to the higher numbers, you have you're starting to see benefits by a few hundred vehicles per approach. This is a similar comparison, but now it's unbalanced demand. So now we have different levels of demand from the different approaches to see if that would make a significant difference. But because this is 100% autonomy, it really does not matter as much. It doesn't matter very much whether you're switching back and forth because you don't have the reaction times. It's the reaction times when you change in the yellow that creates that lowers the capacity when you have frequent switching, which in this case it doesn't matter. So very similar cases. Again, you have reductions in delay and in capacity, and for the amount of total demand is what's the most important. Okay. And this graph shows the effects of the communication range. So we did some experiments with the distance over which vehicles are being detected. And the further away we are able to detect vehicles, the better we are able to adjust their trajectories. So what these graphs show is for different demand levels, 600, 1,000, 1,400, 1,800, and for a range of communication from 500 to 3,000, what were the benefits in terms of delay. And just as a comparison, I'm showing the DSRC, which here it's the screens don't help with this because you can't see exactly where that is, but it's around the 1,500. So the benefits, most of the benefits of the algorithm are realized by the time you get to 1,500. You don't have as much of a benefit with the 500 feet, but then the higher, once you get to the 1,500, you've already realized a lot of those benefits. And so that's encouraging in terms of where the SRC is these days. Let me talk a little bit about implications for when you install this in the field, because yes, we have big improvements in terms of delay in simulation, but when you want to install this in the field, there are additional complications to be thinking about. And I showed you earlier the impact of the communication range, and that the shorter that communication range, the less time you have to adjust the vehicle trajectories. Well, the way we're doing this, remember we have different stages, and so this is one stage, and you're detecting all these vehicles. So let's say that this is 10 seconds. If you're doing this every 10 seconds, the first vehicle that got detected has already traveled a certain distance. So you have to account for that when you're providing an optimal trajectory. You can't wait that amount of time if you're so close to the intersection, because the vehicle may be already gone. So when you're setting up the frequency of the intervals with which you're optimizing, you have to take into control how frequently do you need to be optimizing in order for the vehicle for you to be able to effectively control its trajectory. And then the other element that's important is the speed, because the higher the speed, the faster the vehicle will get through the intersection. You won't have time to do anything with its trajectory. So we developed a relationship between those three as we were trying to look at how frequently should we be optimizing. And so you want to keep it short enough to where you get adequate information, or long enough to where you get adequate information, but not too long, because in that case vehicles are going too far and you're not able to make improvements. When you are just simulating this, because most simulators, you generate a set of vehicles and then you process them. So this may not be obvious when you're doing simulation, but when you are in the field and you're collecting data real time, you don't have advanced information of when vehicles are going to arrive. So in the next stage, we did another, we adjusted the algorithm to be able to account for conventional vehicles. So in this case, if you have conventional vehicles, you have to have signalization the way we have it now. You can still take advantage of autonomous vehicles and connectivity, but now you cannot eliminate the yellow, and you still have some lost time because of vehicles of human drivers. And so in this case we are adding now the yellow. The concept is generally the same, but we are adding the prediction of where conventional vehicles are going to be. So you're trying to predict how they're going to react after you detect them as arriving in the communication range. And so this graph shows results from many scenarios where we tested several things. We tested, first of all, the columns here show different saturation headways. So if you go with 1 second, 1.5 versus 2, the size of the bubble shows the percent of autonomous vehicles in the traffic stream. So the smallest is 0.3 and the largest is 100%. And the color shows the range of communication. The top shows your average travel time, the second shows delay, and the last shows the average effective green. So with the travel time, if you are detecting vehicles over a communication range and you want to change the communication range, you're also changing the length of the link. And so in order for us to have an equivalent, we had to look at delay or travel time per mile, because if you or per 1,000 feet, I think. Because if you change that distance, then your travel time changes. And so what did we learn? First of all, as expected, we have much lower delays if the percent of AVs is higher, because you're able to control a lot more. Also, the saturation headway makes a significant difference in the travel time. The communication range, once you go up to the DSRC range, again, it doesn't change things too much. One of the interesting results was that for higher flow rates, you have more frequent changes in the effective green. So the algorithm was changing the phasing too frequently, or more frequently than what actually the control typically does. This shows a comparison of our algorithm to what Vissim would give us for a similar set of scenarios. So again, consistent with the AVs, we have more benefits realized with higher demands. We're able to have lower percentage-wise delays and higher throughputs. With respect to the effective greens, we have, because you're able to plan based on vehicle arrivals, you have fewer tap outs, so you end up having longer effective greens. And I'm going to show you one last case study we did with kind of the most recent version of the algorithm, which is what it's doing is it re-optimizes more frequently. It keeps better track of vehicles, so you can handle oversaturated conditions. Because if you optimize it the way we did it initially with full autonomy, you optimize once, you provide the trajectories, and you're done. Well, if you start to have conventional vehicles, you need to take into account what you predicted that they're going to do versus what they actually did. And so we are re-optimizing more frequently based on where vehicles actually are. That creates more complication in that now you have to track those vehicles. So it's not enough to just detect them at the communication range, but now you're looking at tracking them, sending that information back to the algorithm, re-optimizing and readjusting if you need to. But that also allows you to look at much higher demands, because if you only optimize once, you have really high demands, you may have queues, residual queues, which you still need to handle. And as your queues grow, then you need to have a way to keep track of that. And so by us re-optimizing more frequently, we're able to get better results even for higher demand scenarios. So the table here, this is the intersection that we analyzed, and the table here shows percent of autonomous connected vehicles in traffic from 0 to 100, and then the demand, and the table shows the throughput that you're able to get with each of them. So, of course, for low demands, it doesn't matter what the percent is, they're all processed 100%. When you go to the really high demands, 850 volume per vehicles per hour per lane, you have at 0% autonomous vehicles. You can get through 568, but when you get to 100% autonomy, you're getting almost 70 vehicles more through for the same demand. The other aspect of this with the algorithm is that what these show is the variability that you have per vehicle. So it shows each vehicle's delay for the different levels of demand. So low demand 250 all the way to 850. And at the top you have 39 to 401. These are the number of seconds that were on the average observed. And so with our algorithm, or when you have autonomous vehicles, you have less variability in the travel times between individual vehicles. Yeah.
Could you put the slide back there?
The previous one?
Yeah. So when the throughput is less than the daily demand, what happens to what's not being processed? Where are these vehicles?
Oh, they're in queue. They're in
So
queue. Yeah.
How long is the queue?
So it will be the remainder. But what this is showing is how much you're able to process. This is the throughput at the stop bar.
Right.
So you still have queues that are being built.
So at the end of 1 hour, you
Yeah.
process 635.
Right. So the remainder will be in queue.
So the remainder of 200 vehicles plus
Yeah. Right.
is in the queue somewhere. At the end of 1 hour, you have 200 vehicles in the queue.
But not the same time.
So that it's
I'm trying to
building.
understand that.
Yeah, it's building. It's building. You have that.
So you accumulate.
You're accumulating,
Ah,
exactly.
okay.
You're accumulating.
So it could be a queue of maybe 4 or 5 vehicles, but accumulated in 1 hour. It's
Right.
all right. Thank you.
So this one shows the variability. As I said, we're able to reduce the variability with the algorithm. So let me talk quickly about our simulation environment. We are simulating autonomy in the loop so that we're able to replicate the way autonomous vehicles, not the way autonomous vehicles would interact would function, but the way other vehicles around them would function in a simulation environment. So we are extracting data from the autonomous vehicle that we have at UF. That data is fed into VISIM, then VISIM operates with autonomy in the loop. It's just simply making adjustments to the simulation does not give you an accurate way of predicting how the traffic is going to operate. I'm quickly going to show you a simulation of kind of a similar concept, but for freeways. Thank you. The bottom shows conventional vehicles, same demand, autonomous vehicles, same demand. What we're doing with autonomous vehicles is we are modifying their trajectories to be able to push them through. They change lanes, we create gaps, and so we're able to improve the throughput, improve operations. It's easier to visualize in a freeway, that's why I'm showing you this, but we're doing something similar with signal control. So again, you are optimizing the movement of vehicles so that you improve the throughput. This is based on a dissertation work by Clark Letter. He focused on freeways. A couple of words on the transition to practice. We've done some testing at the TERL lab in Tallahassee. It's an FDOT facility. And we're getting ready to do some additional testing at the TERL, and also we are installing, we have installed several sensors at an intersection in Gainesville. This is the autonomous vehicle when we were testing it over in Tallahassee. And I'll show you one more video of the test we did in Tallahassee, the FDOT facility has 2 traffic lights. And so we brought our vehicles, the autonomous vehicle, and that's when we first tested the algorithm in a real world environment. So we connected to our signal controller. The signal controller it was connected to the traffic lights. This is the trailer where the autonomous vehicle is, and that's where we were headed. And then we used the drone just to see how things were coming together. And so what ideally you want the vehicle to be crossing the stop bar as the signal is getting green. So we were, this is one of our first tests. Some things worked, some things didn't. One of the issues with hardware is that different pieces of hardware keep track of time in a different way. So it took us a few hours actually a full day to figure that out, but in the end, after a couple of days of testing, we were able to make this work. So we had 6 vehicles at the time. We were able to test the hardware and the software. At this point, we weren't looking at delays or anything like that. We just wanted to make sure that things were communicating, that the controller was displaying what it was anticipated to display, that the vehicles were receiving the information and so on. And I know we don't have much time, so I'll just keep continuing here. So where we are right now is we've installed sensors at an intersection on campus, Gay Lemon and Stadium. It's right outside our office. So we're getting ready to do some testing in the real world. We had to ask to get a permit from FDOT to allow us to do that, and we're going to do it very carefully and really early on a Sunday morning when the campus is empty, because we don't want to take any chances. But we're doing incremental testing in closed area facilities. And one last video I'm going to show you here is, this is one of the approaches of our intersection. I'm going to show you how the trajectory algorithm works. So this is visualizing an optimal trajectory is the dots, and then the actual trajectory is what the vehicle is actually doing. So as every time step, we are optimizing based on the information that we get from the vehicle. And one of the issues that we're working on is the accuracy of all the sensors. And I didn't really talk too much about that, but it's a big issue. How do you use the radar, the video, and the DSRC to combine this information so that you can have an accurate sense of where vehicles are? Because that's of course very significant. One of the FDOT project that we have going on looks specifically at pedestrians, and that's a whole different problem with recognizing pedestrians. We're trying to use LiDAR. A lot of people have used LiDAR, and they've reported different accuracies and so on. When you actually put it in the field, the accuracy is much lower than what has been reported. So what you have in the field is very different than what you're able to test. So several challenges, of course, the sensors, big challenge, the accuracy of the communication, the pedestrians, the intent of where drivers are and where pedestrians are and what they're going to do next. The way we're setting up our algorithm is that if there are miscommunications, the algorithm reverts back to pre-time control. And as I said, we are incrementally improving on the algorithm. We're getting ready to, we're continuing our testing, and so hopefully we'll have a full blown test soon. And just a couple of words on our I Street testbed, which is a collaboration between the University of Florida, FDOT, and the city of Gainesville. And we have several other projects that are developing technologies to improve mobility and safety, particularly safety for pedestrians and bicycles, but also for improving congestion and reducing delays and so on. So if you have interest in that, we have additional information online. And just a list of publications or major publications from which the presentation is based. With that,
Thank you, Lily. Any questions?
yeah.
This is for like a single intersection.
Yeah.
When you have multiple intersections, it'll be probably exponentially more difficult.
Yes, yes. One of my PhD students is starting to look into 2 intersections right now, and it is, like you say, it is exponentially more difficult. Yeah, you have many other issues that you need to take into account. But yeah, it's a very interesting problem. Yeah.
The spacing between intersections, what would be the acceptable spacing for a system of this type to be improving the situation?
Yeah, you need to have at least 1,500 feet or more so that you have that communication. Exactly.
So we're talking about excluding places like Brooklyn and cities.
Yeah, no, it wouldn't work within systems because there's so much interaction between the intersections that it wouldn't be effective. Then you have to go into a systems optimization.
Right.
Yeah.
Then you have pedestrians.
Yeah, right. Yes, there's lots of different complications. This is it's a very complex problem, and even if you take one aspect of it, the sensors, that by itself. You have inaccuracies, you have missing information, that's a big issue. Yeah.
The other thing, this is a selfish question, but part of the testbed, you generate all these trajectories. Are there any plans to make them available at some point?
Yeah, so one of the projects that iStreet has is a data analytics platform. So the idea is that a lot of that data will come online with including all the different projects that relate to that. We don't have anything right now in the works for trajectories. We're just trying to make things work. But there is a plan. We actually have an autonomous shuttle that's now running in Gainesville. Part of what Cranston and Easy Mile are operating in, what part of the requirements is to share those trajectories for the autonomous vehicle.
Okay, thank you, Lily, for coming and presenting. So those of you who are registered for the Women Leaders in Transportation workshop, we invite you to lunch or just around the corner in the